And let's wrap up chapter 3 and cover, here we go, 3.6, the uniform boundedness principle. So in this section, we're showing that a subset, let me read this, throwing the word calligraphy around quite a bit. So we're going to use the same letters, but different fonts in a lot of this. We're considering a subset, calligraphy a subset of the bounded linear operators from x to y. And we're going to show that this subset, calligraphy A, itself is bounded under certain conditions. Now, calligraphy A, it's a set of bounded operators, but just because each of the elements is bounded, that doesn't mean the whole set is bounded. Consider the natural numbers. Every natural number is finite, but the set of natural numbers is not bounded. The text mentions that this boundedness is sometimes called uniform boundedness, as in the uniform boundedness principle. We'll have as hypotheses in the uniform boundedness principle an idea of pointwise bounded. And the statement is set calligraphy A, as described above, a set of bounded linear operators from normed linear space to x to normed linear space y is pointwise bounded if for each x in normed linear space x, the set calligraphy O sub x, that is a set of all tx's where, notice x is fixed, and t ranges over this collection calligraphy A. If this is a bounded set in y for each vector x, then set A is said to be pointwise bounded. So this may not necessarily imply boundedness, it's this pointwise boundedness. And again, we're looking at, actually we'll informally think of these as like cross sections. We're fixing x and looking at the output values. Now it's a collection of output values as the functions vary, as the operators t vary over set calligraphy A. So sort of my thinking here, you can sort of think of the O sub x's as x cross sections of set A. Now we might have a corresponding like a y cross section, thinking very much Cartesian plane here. If we looked at t of set x, that is t of vector x as vector x ranges over set x, this is sort of a y cross section. It's actually the t that's fixed here. So we're taking a particular t and looking at all corresponding output values. Here, we're taking an input value and fixing it and looking at all possible output values as the functions change. So up here, input value is the same. Down here, function is the same. So I say, we might think of this something like a y cross section, but again, it's t that's constant in this little observation here, and not some sort of y, some output. So maybe you want to call these t cross sections, might make a little more sense, but I'm just looking for an informal feel for what the uniform boundedness principle will say. But with this idea of cross sections, the following result, the uniform boundedness principle, simply says if all the x cross sections are bounded and all the y cross sections or t cross sections are bounded, then the set calligraphy A is bounded. So it's very much an idea of cross-sectional bounds imply boundedness of the whole set, which doesn't sound surprising. But the formal statement of the uniform boundedness principle is, if space X is complete, upstairs, we set this up with only normed linear spaces. We needed norms to talk about boundedness. We didn't have assumptions of completeness, but now we're imposing completeness on set X. If X is complete, then a pointwise bounded subset, calligraphy A, of the bounded linear operators from X to Y is bounded. So pointwise bounded implies bounded. Under these hypotheses, let's look at a proof of that, which is not terribly long. It's another one of those I think of as kind of exotic. We're going to look at a direct product and kind of an unexpected term. First, how about we take normed linear space X and let's replace it with its completion. Theorem 2.22, a few sections back, said, this is about a chapter ago, wasn't it? Said something to the effect that every normed linear space has a completion. A completion was a super set. It was a normed linear space of which this is a subspace and this is dense in that space. So anyhow, we're going to a slightly bigger but complete normed linear space. If we show boundedness on the completion of Y, that certainly implies boundedness on Y itself. It's a subset of the completion. Now, one reason we're doing that is we're going to apply the closed graph theorem from the previous section. And the closed graph theorem required us to have Banach spaces on both sides here. And we've said X is a complete normed linear space, so it's a Banach space. And we're considering now the completion of Y, which is also a Banach space. So that's the reason for this movement to the completion. So, as hypotheses require, take A, calligraphy A, to be a subset of the bounded linear operators from X to Y, pointwise bounded. Define the direct product of Y over set A with each space equal to Y. Okay, so maybe we'll run back and look at the definition of direct product. That is, we're defining calligraphy Y to be a product over indexing set calligraphy A of Y. So you might think of it crudely as Y times Y times Y times Y a bunch of times. How many times? The cardinality of the indexing set. And the indexing set is this set calligraphy A. The elements of the direct product are then bounded functions under the sup norm mapping the indexing set into whatever we have here. In all entries, all components, if you will, we've got space Y. Let's look at section 2.10 real quick. Got it hidden in the back. So here's where we define these. We're taking calligraphy A as the indexing set. And in the general definition of just product here, we simply took functions on the indexing set that give outputs in these spaces, these linear spaces, X sub S. Okay, here, the indexing set for us is calligraphy A. The output spaces were always Y. So that simplifies things a little bit. So all the X sub S's we're dealing with are space Y. So they're all the same, is what we were trying to say. Now that was a definition of product. To move down a little bit, we didn't say product, we said direct product, which is subtly different. For direct product, we'll put the sup norm on these functions and throw out all of the functions that have infinite sup norm and keep those that have finite sup norm. So what we have then is functions that map calligraphy A into Y and for which the sup norm is finite. That's the direct product. So that's what we're dealing with. Quick little comment. If each of the X sub S's is a Banach space, then the direct product is a Banach space. All right. For us, each of the X sub S's is Y. The completion of Y, which is a Banach space. So the direct product in our setting is, in fact, a Banach space. Okay, back to the proof. So one more time, so be repetitive here because this is not straightforward stuff. The elements of the direct product are bounded functions under the sup norm. That's when we threw those with infinite norm out, that maps the index set calligraphy A to Y. We'd have to deal with this somehow component-wise in general, but we've taken a product of Y with a Y with Y with Y with Y all the time. So I can tell you exactly where those live. I don't need some X sub S stuff here. All the X sub S's are Y. So we have bounded functions mapping the indexing set calligraphy A to Y. And calligraphy A consists itself of bounded linear operators. So here we have a function that maps bounded linear operators to this Banach space capital Y, completion of capital Y. Okay, so let's look a little more at that to try to make heads and tails out of what's going on. We're going to define, as I warned, here's the awkward verbiage. My symbols are so convenient. Calligraphy T of X takes in bounded linear operator capital T and gives out capital T of X. So we're defining this for all T in indexing set A. So what we have is indeed capital T of X maps elements of calligraphy A, like capital T, and gives out elements of Y, like T of X. T of X is an element of Y. Right. T, being a bounded linear operator from X to Y, takes in elements of X and gives out elements of Y. So yeah, this calligraphy T of X does indeed take linear transformations in calligraphy A, and gives out elements of Y. So calligraphy T of X maps indexing set calligraphy A to normed linear space Y, as it should as an element of the direct product. T has an input value of X, and T produces an element of the direct product, an element of calligraphy Y. So T of X, here's how T of X acts on elements of A. So T of X itself is an element of the direct product. The elements of the direct product are what? Bounded functions mapping calligraphy A into Y. And that's what we have. We need to show some of the boundedness stuff. But we've got the mappings doing the right thing. Calligraphy T maps X into the direct product. Calligraphy T of X maps A into Y. And that's what we needed for elements of the direct product. Okay, here's a definition. We'll be seeing this in the future. So calligraphy T of X on capital T produces capital T evaluated at X. Okay, we've hypothesized pointwise bounded. So for every X, calligraphy O of X, so pointwise boundedness of calligraphy A, that means O sub X is the norm of T of X, where T ranges over calligraphy A. This is a bounded set. We fixed X, says for each X, we fixed X and allowed the functions to change. That's how we dealt with the O sub X things. These were X cross sections, as I called them. So these O sub X's, these are all bounded for each X. That's what pointwise bounded means. Let's find a bound on this O sub X. We know one exists. That's a hypothesis. Let's call it K sub X. So O sub X is bounded by K sub X. Now, the X's change, the sets change, and the bounds change. So we don't have any kind of uniform boundedness yet. But we do have these, cross-sectional bounds. So if we take calligraphy T of X in the direct product, calligraphy Y, the norm of calligraphy T of X would be, well, let's see, this takes in capital T's, transformations in set calligraphy A. So definition of the sup norm would be the supremum of this thing acting on an input. The thing is calligraphy T of X, and the inputs are T's, where the T's come from calligraphy A. And if we're doing an operator norm, we need those inputs to be unit vectors. So we need operator T to be 1 in norm. And geez, we could try to track down all the norms we have here. That's the operator norm. I know that. We're dealing with bounded linear operators. So this is the norm being used on the T's. I'd have to think a little bit about where these things are to see exactly which norm we're dealing with. But calligraphy T of X has this norm that is the supremum of the norm of regular old capital T of X. Remember, previous slide, calligraphy T of X acts on capital T to produce T of X. That was the very definition of the calligraphy T of X. So we simply substituted in there, copied all this stuff down. Why? That is roughly what we have up here. We know this set, O sub X, is bounded, norm of T of X, where T is an element of calligraphy A. And hey, we've got the norm of T of X, where T is an element of calligraphy A. We've also got an added condition. So since K of X is a bound on this set, and K of X is a bound on this subset, the added condition of calligraphy of norm of T equals 1 says this is a subset of that. So anyhow, an upper bound of that is also an upper bound of this. And the norm of calligraphy T of X is less than or equal to K sub X. So calligraphy T of X is a bounded function on calligraphy A, and that holds for each X. So there's boundedness of calligraphy T of X, and I'm mildly worried. One more time. We got from here to here, how calligraphy T of X of T is defined as this. Let's go back to the previous slide and look at that real quick. Right, calligraphy T of X of T is simply T of X. The parentheses, when I've applied a function to something, I'm using possibly a bit inconsistently. The calligraphy T is also acting on X to produce something. I could view this as a composition of functions if you like. But we did have calligraphy T of X acts on T to produce T of X. Back to where we were, next page. That's the substitution we've made here. The only difference is I don't have parentheses around the capital T. Okay, so calligraphy T of X is a bounded function. That holds for all X. We're not after boundedness of calligraphy T of X. We're after boundedness of set A. So we need to shift over to the boundedness of set calligraphy A. We're going to do so using the closed graph theorem. We'll go back and look at the closed graph theorem here in a second as well. What we need is a sequence of points in the graph of an operator. So what we're going to consider is a sequence X sub n of elements of norm linear space X that converges to vector X, and a sequence calligraphy T of X sub n, a sequence in set calligraphy A, which converges to some mapping of A into Y. So we've got part of the graph of calligraphy T. We've got input values and we've got output values. The input values are X's. The output values are, well, they're bounded linear operators, but that's what the output is. Maybe let's take a quick peek at the closed graph theorem. It was just the last section, but this is pretty involved stuff. It says T, a linear operator from X to Y, where X and Y are Banach spaces. We made a comment about earlier that we're taking the completion of Y. That gives us the Banach space stuff. So we can legitimately apply the closed graph theorem in this setting. T is closed if and only if it is bounded. And closure of T, you will recall, means closure of the graph of T. And the graph of T was all input and output values of T. We had T mapping X to Y here, so we had ordered pairs. That's the reason we're looking at what we're looking at now. We've got inputs and outputs. Maybe they're not X's and Y's, they're X's and something else, they're X's and bounded linear transformations. But anyhow, they're inputs and output values. So if the graph is closed, then the operator is bounded and conversely. So T is closed if and only if T is bounded. T is closed, really the definition was the graph of T is topologically closed. Back to the proof. So we're taking some X sub n's and some calligraphy T of X sub n's, some inputs and some outputs of calligraphy T. So suppose we get the sequence X sub n to converge to X, and we get this sequence, calligraphy T of X sub n, to converge to something, some G, a function that maps calligraphy A to Y. So this would be something in the direct product, calligraphy Y, we denoted it as. We're going to show that G equals calligraphy T of X. So in other words, the limit of this sequence must be T of the limit of the sequence of the X sub n's. So if the X sub n's converge to X, then this stuff must converge to T of X. That's what we're showing. So we're taking G to be T of X. We're going to show that that actually equals calligraphy T of X. So take G, apply it to whatever it's applied to, and the things it's applied to are elements of calligraphy A, that is, bounded linear transformations from X to Y. So take such a transformation, let's denote it capital T, as we've been doing. Now, we've assumed that the T of X sub n's converge to G. So we can take the G and write it as a limit as n approaches infinity of calligraphy T of X sub n. Applied that to T, that's the convergence assumption of this sequence. What is calligraphy T of X sub n applied to T? It's the same thing we have up here. Calligraphy T of X sub n applied to T. So we got a sub n down here instead of an X. That takes transformation T and applies it to this thing. It outputs T of X sub n, T of X sub n in this case. So that's what this is by definition. Calligraphy T of X sub n of T is T of X sub n. That's how we define calligraphy T. So good news, we've dumped the calligraphy fonts here for a few lines at least. And evaluation. So now we're looking at T of X sub n's, but we can take that limit inside. You telling me capital T is continuous? Yeah, it's bounded. T is from calligraphy A, and calligraphy A is a set of bounded linear transformations between X and Y. And recall, also I think we need Bonnot spaces for this, bounded linear transformations are continuous. Theorem 2.6 gives us that, and it's the continuity that allows us to take the limit inside. So boundedness implies continuity and limits go inside. What's the limit of the X sub n's? The X sub n's converge to X. So we'll make a substitution there and we get to T of X. Need a little slide break here. We're trying to show whatever G does to capital T, calligraphy T of X does the same thing. We're trying to show those are equal. All right, so let's copy this last line again. So we left off with G of T is T of X, and there was the reasoning. Hey, but wait, T of X is calligraphy T of X applied to T. The very definition of how this thing behaves is it produces T evaluated at that. It produces T of X. So T of X equals this by the definition of calligraphy T, and look what you got. As long as T was an element of calligraphy A, then G does the same thing to it that T of X does, calligraphy T of X does. So these are equal on calligraphy A. So if we take any sequence of the form x sub n, calligraphy t of x sub n, input values and output values, this will converge to x, calligraphy t of x, in the space x times calligraphy y, x times a direct product, because we'd use the sup norm on that direct product. If we use a sup norm and we have the pairs converging, then each of the constituent parts of the pair must converge. That is, we have, under the assumption that this occurs, we must have x sub n approaches x, and t of x sub n approaches calligraphy t of x sub n approaches calligraphy t of x. So any sequence of points converging to an element of set A, or converges to an element of set A, and that is calligraphy T is closed. Definition of closed in terms of closed sets contain limit points. We had a bunch of conditions equivalent to closed sets, and this was one of them in terms of dealing with sequences. Sequences of pairs, since we're dealing, I'm thinking in my mind, we're kind of dealing with a two-dimensional thing when we deal with graphs, maybe not exactly two-dimensional. We haven't even defined dimensions for a lot of this stuff, but I'm still making analogies with the Cartesian plane in my mind. But we've taken a sequence that converges. We've got something in the graph, and so the graph is closed. If the graph is closed, as we just saw, the closed graph theorem tells us the associated function for which we're considering the graph. I guess I look right there. We're considering input values and output values from calligraphy T, So it's the graph of calligraphy T. So the graph of calligraphy T is closed and calligraphy T is bounded. That's the closed graph theorem. So calligraphy T is bounded. We're almost done. So what are we trying to show? We're trying to show set calligraphy A is bounded. Well, calligraphy T is bounded. That is, calligraphy T defined to be the supremum of the norm of calligraphy T of x, where x ranges over norm linear space x, and definition of sup norm, we take unit vectors, norm of x equals 1. And this, that's some parameter k that's finite. There's the bound on calligraphy T. So if we take any t, bounded linear transformation, capital T, an element of calligraphy A, and we take any vector x, a unit vector with norm 1, we have calligraphy T of x applied to capital T. That is, by the definition of calligraphy T of x, capital T of x in norm. You know, this thing is bounded by k, if we put a unit vector in. So this thing is bounded by k. This T is an arbitrary element of set A. So we had similar things bounded by k sub x's before. Well, now you got it bounded by a k that doesn't depend on the x's. So this works for all x's, well, unit vectors in the norm stuff, and works for all t's in A. So we have the norm of t of x less than or equal to k for all unit vectors. And so the norm of t is less than or equal to k. And that bound works for all t in calligraphy A, for all capital T in calligraphy A. That is, finally, calligraphy A is a bounded set. It's bounded in norm by capital K. So that's the reason we went to the trouble of introducing calligraphy T. The norm of that operator, calligraphy T, gave us a bound on the set calligraphy A. And the claim was, if set calligraphy A is pointwise bounded, then it is bounded. And that was the uniform boundedness principle. Okay, there's only 2 results in this section. That one, the proof wasn't long, but I would certainly argue that it wasn't easy either. The final result here is given the uniform boundedness principle is not so bad. Sometimes uniform boundedness principle is called the Banach-Steinhaus theorem, though I'm not an expert in this stuff, but I'm more familiar with the uniform boundedness principle terminology. The next result is an application of the uniform boundedness principle that shows that the bounded linear operators from x to y is closed under pointwise limits. So closure under pointwise limits is going to follow from uniform boundedness principle. The formal statement, let's just go to the proof. The formal statement is, suppose that sequence T sub n is a pointwise convergent sequence of bounded linear operators from Banach space X to normed linear space Y. That is, to make more specific what that pointwise convergent stuff means. For every X, a vector in normed linear space capital X, the sequence T sub n of X, so these would be Y values, output values, the sequence T sub n of X converges to an element T of X in Y. So if that holds, then T itself is linear and T itself is bounded. Good news is there's no calligraphy fonts in this one. That was all taken care of by the uniform boundedness principle. Okay, an assumption of pointwise convergent sequences in this sense, implying T is linear and T is bounded. Linear is easy. Take an alpha X plus beta Y, a linear combination of vectors in capital X, and apply T to it. Well, you know, T is the limit of the T sub n's. We set things up such that the T sub n's are pointwise convergent. So for every vector, T sub n of X converges to T of X. So this is T of something, then it's the limit as n approaches infinity of T sub n of that something, any vector in the input space, in space capital X. We have the limit property holding. Now we're in business. The T sub n's are linear, so use the linearity of the T sub n's. Limit of a linear combination is a linear combination of the limits, properties and limits from calculus 1. And now we know the limit as n approaches infinity of T sub n of X will be T of X. T sub n of X converges to T of X. Similarly over here, T sub n, little typo there, that should be a Y, shouldn't it? T sub n of Y approaches to T of Y. We have the T sub n of Y's up here. I'll get that corrected and posted online. And so we've shown T of the linear combination is a linear combination of the T of's. That is, T is linear. Now for the boundedness, well, the boundedness is not too hard given we have the uniform boundedness principle. For boundedness, take X as any vector in normed linear space capital X. The sequence T sub n of X converges, hypotheses, and so is bounded. Bounded sequences are convergent sequences are bounded. This is a convergent sequence, and so it's bounded. We can justify that with a couple of parts of Theorem 2.9, which talk about Cauchy sequences, but you should be happy to accept that convergent sequences are bounded. That's certainly the case in normed linear spaces, but for the record, there's some justification of it. So T sub n, for n a natural number, so it's a set of bounded linear operators. This is a pointwise bounded set. Each of the T sub n's are bounded. That doesn't mean the whole collection is bounded. But what we get out of that is for each X, a vector in normed linear space capital X, the set O sub X equals T sub n of X. As the functions change, as the indices change, X is fixed, and these things change. This is a bounded set. But the uniform boundedness principle says if you got all of these things bounded, then there is a K such that norm of T sub n is less than or equal to K for all such operators. That is, for all t sub n's in this case. So there's the application of the uniform boundedness principle. We got the O sub x's. We've got the proper setting that X was a complete norm linear space, Y was just a norm linear space. Though in the proof of the uniform boundedness principle, we did go to its completion, but that need not be the hypotheses. So we're good. Hypotheses for the uniform boundedness principle hold, and that gives us the bound on the collection. So might call this calligraphy A in the notation of the uniform boundedness principle. So if we take any unit vector x, then we have the norm of t of x. That would be the norm of the limit as n approaches infinity of t sub n of x. We've hypothesized that t of x is the limit of such a sequence. We can take the norm inside the limit because the limit is continuous. We've done this several times before. It's Theorem 2.3 part C. The norm is continuous. And we saw that t sub n of x for any n was bounded by k. So we get this limit bounded by k. The norm of t of x is less than or equal to k for any unit vector lowercase x. So when we take the operator norm of t, we're trying to show now t is bounded, so time for the operator norm, so the n must be near. The operator norm of t, that is the supremum of the norm of t of x, where x is a unit vector, that must be bounded by k as well. Each of the elements of that set is bounded by k, so the supremum is bounded by k, and the operator norm of t is less than or equal to k, and that's boundedness of t as claimed. So that processes the uniform boundedness principle. That completes chapter 3. And now on to chapter 4, and now on to the really cool stuff, the really geometrically intuitive stuff. That's what I mean by cool. Hilbert spaces. So I will see you in chapter 4, and we'll do some Hilbert space stuff. Have a nice day.